is completing the story for the solution of polynomial congruences. In the previous chapter, we focused on the simple case of linear congruences, and as I reviewed in the last lecture, we reached a complete understanding of linear congruences, which was encapsulated in theorem 6.3 and the previous results. Okay? By examining the coefficient on the x in the linear congruence, comparing it with the modulus n, looking at the greatest common divisor, looking at what that greatest common divisor does with the constant term b, you can decide whether or not there are solutions. If there are solutions, you know exactly how many of them are, and the result gives you a recipe for generating the solutions, generating representatives of the congruence classes of the solutions of the original congruence. So that's all well and good for linear congruences, ones where the polynomial is order what? Something times x plus a constant. And also in that chapter was the Chinese remainder theorem, which provided a tool which we're going to use to put together solutions for general polynomial congruences. Okay, we discussed that last time. We'll be coming back and engaging with it again when we're describing how to solve our polynomial congruences in general. So now we're moving on to the next chapter, polynomial congruences 2. And we've got straight away a prominent result, theorem 7.1, which is a theoretical result about the number of solutions that a polynomial congruence might have. Okay, so that's what we're going to look at today. After that, so there's that main result, theorem 7.1. There's a little corollary to it. But then the next major piece is another theorem which we're not going to prove, or we're just going to use the statement of it, which basically provides the algorithm for finding solutions to a general polynomial congruence. So this is quite a technical kind of result, but it tells you how to go about constructing solutions to a general polynomial congruence, importantly, modulo a prime power. So not for a general modulus, but for the special case where the modulus is a power of a single prime. But of course, powers of single primes, they're the building blocks of any integer via the fundamental theorem of arithmetic. Every integer factors into, uniquely, a product of factors, each of which is a power of a single prime. It's prime factorization of a number. Okay. So using this key result about how we build solutions modulo a prime power of a prime, this, together with the Chinese remainder theorem, gives us then a procedure for solving a general polynomial congruence, which is outlined in section 7.3. Okay. But we come back to the start of the, such a quick trip through the chapter. We come back to the start of the chapter 7.1, and there's a little discussion paragraph here, and then I'm going to take us through the proof of theorem 7.1 on the visualizer. It's mostly written out there in the notes, but I just want to explain through it step by step and maybe provide a little bit more detail here and there as to what's in the notes. So what we do is we go back, we recall one of the initial examples we looked at when we were investigating the type of situations you might have for solutions of polynomials, okay? And we won't work through the examples in detail, but we'll just look at one particular example. So for instance, back in chapter 6.2, we looked at this polynomial congruence, x squared minus 1 congruent to 0 modulo 8, and we found that it had 4 solutions. 4 solutions to this modulo 8. They were, just off the top of my head, 1, 3, 5, and 7. So 1, 3, 5, and 7, those congruence classes modulo 8, when you square them and subtract 1, you always get something congruent to 0. Something which is divisible by 8. And that's kind of interesting because there you've got more solutions than the degree of the polynomial. We also saw other examples, well, in example 6.1, and also plenty of examples in our linear congruences chapter of congruences that maybe have no solutions at all. So sometimes you can write down a polynomial congruence, even a simple linear one, and it just has no solutions at all. So sometimes there's lots of solutions around, 4 solutions, compared to the degree of the polynomial. And sometimes there's very few solutions, or none at all. Okay? So we already know that we're in quite a different situation compared to polynomial equations. Okay? Because as we referred to when we started chapter 6, for polynomial equations, at least over the complex numbers, we always know that you can find, if you're counting multiplicities of solutions, counting multiplicities of groups of the polynomial, you can always find the same number of solutions for the polynomial as the degree of the polynomial. So a polynomial of degree 5 has 5 complex roots, albeit some of them may be single complex numbers occurring with multiplicity bigger than 1. Okay. So theorem 7.1 goes some of the way to establishing a corresponding result for polynomial congruences. So let's just read the result to begin with. And it's not telling you exactly how many solutions the polynomial congruence has, but it's giving an upper bound. So it's putting a limit on the number of solutions that the congruence might have. Okay? We know it can't tell you the exact number because we've already seen examples where there are no solutions at all. So it's never, you'll never have a completely general result telling you exactly how many solutions the polynomial congruence has linked to the degree of the polynomial. So this applies in, now it is a special case, it's the special case when the modulus is a single prime number. Okay? So it is quite restrictive in that sense. So the modulus is a modulus p. Of course, anywhere in number theory we write p. P is a prime number. It'll deal with any polynomial. So we think of f as quite a general polynomial of degree n. See there, it's written down as it's a degree n object in that it's got powers of x all the way up to x to the power n. So you certainly call that a degree n polynomial. But in order to call it a degree n congruence, we want something a little bit stronger. To be genuinely of degree n as a congruence, it must be that the coefficient of x to the power n, which would be this coefficient a sub n, the a sub I is the coefficient of x to the I. We need to know that that a sub n is actually non-zero when you consider it modulo p. So you want your leading coefficient of the polynomial, an, to be non-zero modulo p. So that means p does not divide. It's not a multiple of p. So if that leading coefficient was a multiple of p, while you would say the polynomial equation fx equals 0 has degree n, but you wouldn't say the polynomial congruence has degree n, because that coefficient of x to the power n, considered modulo p, would be 0. So this condition that the leading coefficient is non-zero modulo p, that just means that it's genuinely of degree n considered as a polynomial congruence. Okay? And the result is that if it is of degree n as a polynomial congruence, then it has at most n solutions. It's not telling you the exact number of solutions, but it's giving you an upper bound. So the degree of so there is a link between the degree of the polynomial and the number of solutions, but it's a lot weaker compared to polynomial equations. Here, the degree of the polynomial is just providing an upper bound on the number of solutions that there might be. Okay. Now the proof here, it's substantial. The proof is just over a page long. And it's quite nice and satisfying in that you've got a number of things going on. There's overall it's a proof by induction, but hidden within the proof by induction is a little bit of a proof by contradiction as well. So it's using quite a lot of interesting proof techniques. Okay. Any statement, any queries just about the statement, just about understanding the statement we're looking at. Okay. All right. So let's have a go at talking through the proof. Here. So this is theorem 7.1. So f of x is our polynomial of degree n, and it's genuinely of degree n when we consider it as a polynomial congruence. So the prime number p does not divide the leading coefficient of the polynomial. Then it's saying that this congruence, f of x congruent to 0 modulo p, has at most n solutions. Okay, so the proof is by induction on n. N greater than 1. Okay? N greater than 1 being the degree of the polynomial. So the base case is n equals 1. So in that case, you're looking at f of x, well, it's just a1 times x plus a0, congruent to 0 modulo p. Well, that's a linear congruence, okay? We've already dealt completely with linear congruences in the previous chapter. Now we also have this extra condition that p does not divide a1. Okay? Remember, p does not divide the leading coefficient. So in the base case for linear polynomials, p does not divide the coefficient a1. So i.e. the greatest common divisor of a1 and p is what? It's a coprime. P is a prime number. It only has those two divisors, 1 and p. So p does not divide a1. It's the only common divisor between p and a1 is 1. It's a coprime. So a1 inverse mod p exists. And only one solution, so it's a single solution, which is x congruent to a1 inverse, so minus a1 inverse a0 mod p. That's the single unique solution that there is in this case. Okay? So the result is true. The result is true for the base case. Okay? The polynomial has degree 1 and there's one solution. So the degree is certainly an upper bound on the number of solutions. Okay. Okay, so that's the base case dealt with. So now we can proceed with our proof by induction. It's just regular induction. It's not strong induction. So we assume that the result is true, well, for all such polynomials, of degree k. So any polynomial f, degree k, so that goes up to x to the power k, and if its leading coefficient is not divisible by p, it has at most k solutions. Yeah, it's worth spelling that out. Okay, it's true for all such polynomials of degree k. They have at most k solutions. So now what are we trying to do? Now we're attempting to prove the same thing for polynomials of degree k plus 1. Yeah, so that's what you have to do in a proof by induction. You assume the result is true for some value, some general value in the domain, and you try and prove that that assumption implies the truth of the next case. Now we try and prove, we try and prove the result for all such polynomials. When I say all such polynomials, I mean all the ones whose leading coefficient is not divisible by p. So for all such polynomials of degree k plus 1. So how are we going to do this? How are we going to prove this thing for every possible polynomial of degree k plus 1. So that's quite a daunting thing to do. Polynomials of degree k plus 1, there's a lot of them, an infinite number of them, an infinite number of choices for the coefficient. Well, sorry, maybe not an infinite number of them because we're dealing modulo p's. There's only a finite number of possibilities. There's going to be a large number of them. We certainly don't want to try and deal with every single one. So we're going to prove this in a clever way. We're going to go about it in a neat kind of way. We're going to prove it using proof by contradiction. So this will be done, this meaning this trying to prove it for k plus 1, this will be done using proof by contradiction. Okay, but our proof by contradiction is now embedded within an induction argument. It's often the way with substantial proofs by induction that you prove the significant step, prove the induction step using proof by contradiction. So what we do is we assume that this result is false. So we assume that it's not true for all polynomials of degree k. But that means we can give ourselves a single contradictory polynomial. Okay. So we assume, what about, I think I've called it G. So we assume we have at our disposal a polynomial G of degree k plus 1 that has, now remember, the result says the degree is an upper bound for the number of solutions. So if this one is a contradictory one, it means it must have too many solutions. It must have solutions that are greater than, must have a number of solutions that is greater than the degree. So assume we have a polynomial G of degree k plus 1 with at least k plus 2 solutions. Okay, so greater than the degree of the polynomial. So i.e., we've got a polynomial g of x, which goes up to, so call it bi x to the power I, and its degree k plus 1. So it's going from I equals 0 up to k plus 1. Multiples bi times x to the power I all the way up to k plus 1. And this has at least k plus 2 solutions. So the solutions, I'm going to denote them as x0, x1, etc. If there's at least k plus 1 of them, at least k plus 2, that means I'm going all the way up to xk plus 1. There's k plus 2 numbers there in that list, because I begin at 0, up to k plus 1. These are solutions modulo p to this problem of g of x congruent to 0 modulo p. And the solutions are, I'll just emphasize, for the xi are distinct. Distinct modulo p. They're distinct congruence classes modulo p. So you've got at least k plus 2 solutions. Now there can be no such polynomials, okay? Because the result of the theorem says there aren't. We're in the middle of a proof by contradiction, so we've assumed that there is one. So we will show, that's why I'm just putting in a lot of effort just to present this correctly and kind of orient it in front of you correctly. We will show that this G, this polynomial with these supposed solutions, that this G is a contradictory object. It cannot exist. Contradictory object. It cannot exist. Meaning that it contradicts. The way we're going to show that it can't exist is it's going to contradict the induction assumption that we just made. I.e., it contradicts the assumption. Nice that this landed here. this assumption back up here. So that's going up to the induction assumption we just made. It contradicts the assumption we just made. So before we get stuck into the details of proving that it's contradictory, we first just have to recognize the overall logic. We're going for proof by induction on the degree of the polynomial. So the base case is linear polynomials. They're already proved by the previous results. So now at the top of that page, visible page there, we assume the result is true for every polynomial of degree k. We're now going to try and prove it's true for every polynomial of degree k plus 1. We do that deduction, that true for degree k implies true for degree k plus 1. We're doing that deduction using proof by contradiction. So we assume that a polynomial exists that violates the result. So it's a degree k plus 1, and it has too many solutions. It has at least k plus 2 distinct solutions. So we name the polynomial, and we name all its parts, coefficients bi, and we name the solutions. Solutions x naught up as far as xk plus 1. Maybe it has even more solutions. But in order, the minimal requirement for it to be contradictory is that it contains k plus 2 solutions. So there they are, x naught through xk plus 1. So in order to show that this contradicts the induction assumption, how will we do that? We will extract from g, from little g, a polynomial of degree 1 less, of degree k, that also has too many solutions. 2 T00 that also has too many solutions, i.e. at least k solutions. Sorry, at least k plus 1 solutions. We just assumed that every polynomial of degree k has at most k solutions. So if we can offer up one that has at least k plus 1 solutions, that would be a glaring contradiction. Something contradicting the assumption just made. So what does it mean by extracting a polynomial from G? Well, how do you extract polynomials from each other? You do some kind of factorizing exercise. Okay? Some kind of factorizing exercise. So there's a little bit of a trick. So this is a kind of factorizing exercise. And the trick is to define a new polynomial g of x, which is defined as our original little g of x minus whatever the value of g is at, we just choose one of the solutions. We just choose the first solution, x naught. And we construct this new polynomial, capital G of x, which is the original polynomial little g of x, minus this special value g of x. Well, using the definition of G, this is summation bi xi minus the summation bi x naught I. Yep. Little g is a polynomial, so g of x is that summation. G of x naught is this summation over here. These are two summations. They're both over I from 0 to k plus 1. I from 0 to k plus 1. So we can deal with this with just a single summation. You take out the bi, it's going to be bi multiplying into xi minus x naught to the power I. Now there's a special case here. You see when I is equal to 0, the term over here is b naught, and the term over here is b naught. So in the special case where I is 0, as it is for the constant term of the polynomial, you'll just have x0 minus x naught. Well, that's just 1 minus 1. It's just the number 0. So I can drop off. I don't have to start this summation from I equals 0. I don't have to because the term when I is equal to 0 is just the integer 0. So I just discard it, and I can instead begin this summation from I equals 1. Now, what is the great thing? Remember, this is some kind of factoring exercise. Somehow we want to extract out of polynomial little g another polynomial little h, which is a self-contradictory thing. It's going to have too many solutions because g had too many solutions. Can anybody spot, can you spot any way to start factoring what you have in front of you? Well, there is a way, because what we're adding up there is loads of terms which they're a difference of I powers in each case. Okay? X minus x naught when I is 1, x squared minus x naught squared when I is 2, x cubed minus x naught cubed when I is 3, etc. So the term you're adding up there is always a difference of I powers. So remember that a difference of I powers, I'll write it out just in different notation so it's not, you won't mix it up with that. If you have a ui minus a vi, where I is something bigger than or equal to 1, this always factorizes. And one of the factors you can take out is always the difference u minus v. The other factor is a sum of products uv, and the top power will be I minus 1, and then this will be I minus 1 minus j, and this j will go sorry, scrub that, that's a j there. That j goes from 0 to I minus 1. So it's u to the power j times v to the power I minus 1 minus j. The point is it factorizes. And it factorizes in a way that you can subtract the factor u minus v out of it. So we're going to use this factorization on capital G of x. So capital G of x, we can take out, so out of all of these comes the factor x minus x naught. Now I'm not so interested in keeping track of exactly what the other factor polynomial looks like. So you can see here, I've just written it down as a h of x. So the h of x is the summation of the bi times this summation over all possible values of I. Okay? It's just all the stuff that's left behind when you take the factor x minus x naught out of each of those terms there. Okay? But I just need to record a few things about it. Where h of x is a polynomial. Now, it will have degree k. It has to have degree k. See, capital G is degree k plus 1, and we're taking out an order 1 term, so the bit that's left behind must have degree k. Its leading coefficient will still be the same leading coefficient that capital G of x has, namely bk plus 1. So this still satisfies the fact p does not divide the leading coefficient. I could, if I wanted, record exactly what h of x looks like. It's just the summation over I times v of I times this summation over j. But we don't have to keep track of it. We just have to keep track of these facts about it. H is degree k. It's got leading coefficient b k plus 1. b k plus 1 is not divisible by p because it's one of these polynomials, genuinely. Well, it was a coefficient of little g to begin with. Yeah, but notice now. So now we're going to start to look at what solutions little h has. So notice that for each I from 1 up to k plus 1, g of xi, which by definition is little g of xi minus g of x naught, this is always congruent to 0 modulo p. Why? As both xi and x naught are solutions to little g of x congruent to 0 mod p. So when you evaluate capital G at these little xi's, which were the solutions, all the other solutions, apart from x naught, all the other solutions to the polynomial little g, these are still solutions of capital G. Or in other words, if it's congruent to 0 modulo p, it means that p divides the value. But that means p divides, see, the value of capital G of x, it's also equal to this thing here. So it's xi minus x naught times h of xi. Now we're going to drag something else from before. P divide, see, this after all is just capital G of xi. This capital G of x is this expression here. These little xi, if you look further back up the page, these were distinct modulo p. These were all representatives of different congruence classes modulo p. So the xi's are all distinct from each other modulo p. So that means none of these brackets, xi minus x0, where I starts from 1 and goes to k plus 1, none of those brackets, xi minus x0, none of those are divisible by p. None of those are congruent to xi is never congruent to x naught mod p, i.e. p does not divide xi minus x naught for any I from 1 to k plus 1. They're distinct. Okay, but fundamental thing about prime numbers, if a prime number divides a product, Euclid's lemma, all the way back a number of chapter it goes, but it's fundamental. If a prime divides a product, it must divide one of the factors. You can't split up the presence of p, a little bit of it in one factor, a little bit of it in another, because it's a prime number, it can't be split up. So this p, if it's dividing this product here, but it turns out that it never divides this first factor, it means it must always divide the second factor, because if p is a prime number. So p does not divide this bracket here, xi minus x naught, because these are distinct congruence classes modulo p, so p must divide h of xi for each I from 1 to k plus 1. So in other words, these are solutions to h of x equals 0. H of xi is congruent to 0 modulo p. Each I between 1 and k plus 1. So this H is a poly of degree k, we agreed that, with at least k plus 1 solutions. Okay, but that rings alarm bells because such a thing cannot exist, because we assumed it could. Okay? We assumed that those kind of things could not exist. So the existence of them contradicts that assumption. So if we've assumed that these kind of things must not exist, these kind of things, little h cannot exist. But where did little h come from? Little h came. Remember, little h came from the little g, which also had too many solutions. The little g was of degree k plus 1. So this here is a contradiction. It contradicts our inductive hypothesis. But the little h came logically from little g, so little g must be a contradiction. So the existence of little g, what we've shown is it contradicts the induction hypothesis made earlier. So that means if you make that induction hypothesis, it implies that such little g's can't exist. These little g's are ones that have too many solutions. Polynomial degree k plus 1 that have too many solutions. So there can't be any polynomials of degree k plus 1 with too many solutions. So therefore, the resultant lemma is true for polynomials of degree k plus 1. They can have at most k plus 1 solutions. So polys of degree k plus 1 have at most k plus 1 solutions. We did the base case. That's the inductive step. It's true for degree k. It must also be true for degree k plus 1. Therefore, by the principle of induction, it's true for every possible degree of polynomial, so it's true for all polynomials. So theorem is true for polys of degree n, for all n bigger or equal to 1 by the principle of induction. So the theorem is true. The theorem is true for all polynomials. Okay, so that's really nice. I think it's a really nice workout of proof techniques. It's an induction argument. Within it is a substantial proof by contradiction for the inductive step. We've seen a bit of polynomial factorization thing, factorizing, just using the known factorization of differences of powers. Euclid's lemma arises again. Fundamental fact of prime numbers. If a prime number divides a product, it must be present in one of the factors of a factor. You can't split it up. So it involves it involves all the a lot of classic stuff. But it also gives us a very nice result. We now know. In the next lecture, we're going to see. I don't want to start squeezing in now, but so in the next lecture, we'll see exactly how we solve polynomial congruences in general. And it's based on taking the general modulus and looking at the prime factorization. But at least now we know we've got a cap on the number of solutions. So that at least provides us with a safety net so that when we start finding solutions, we'll know when we've found them all. Because as soon as we find this upper bound of number of solutions, we'll know there can't be any more. So it'll give us, it will allow us to make progress with that exercise. Okay, so in our next lecture, then we should finish off that chapter, which will then free us up then for the final chapter on quadratic residues.